And the first one is called nucleophilic substitution reactions. We're going to learn two types of mechanisms, an SN1 and an SN2, where the S stands for substitution and the N stands for nucleophilic. And the 1 and 2 are kind of a description about the mechanisms it goes through. And then we're going to talk about elimination reactions and the same type of thing. There's going to be something called an E1 and an E2 reaction. All right. But first, let's talk about what is an organohalide. We've also talked about them as alkyl halides, but it's basically an organic compound that contains at least a halogen, all right, or a carbon-halogen bond. All right, and we've talked about halogens are fluorine, chlorine, bromine, or iodine. It can contain many halogen bonds. There's lots of examples. Some examples are fire-resistant solvents, CFCs, pharmaceuticals. Actually, Teflon is a pretty common. It's a polymer. A polymer means it's many units hooked together. So what Teflon is a carbon. It's this huge chain of carbons. You know, we're talking trillions and trillions of carbons. So these just keep going on and on and on, and all these bonds are fluorine. All right, fluorine is very reactive in itself, but once it forms a bond with carbon, it's virtually, you can't break that bond. Okay, and fluorine won't react with anything after that. So that's kind of why it's great to use on pots and pans that don't stick to anything, because they don't react with anything. If anything gets close enough to it, it doesn't do anything. It just kind of slides off. So Teflon is an example of an organohalide. So section 7.1 talks about naming of alkyl-halides, and we've already talked about this, so this shouldn't be anything new, but pretty much you find your longest continuous chain, you find its parent. If it has a double or triple bond, then the double triple bond is the parent, and then you number from the end nearest any substituents. It doesn't matter if it's a halogen or an alkyl group. As you can see, we have two examples here, where the halogen is closer to the end. Here we start numbering on this side because the second carbon has a substituent. On this one, we start numbering on this side because the second carbon has a substituent. So in this case, this would be called 2-bromo 4,5-dimethylheptane. This one would be 5-bromo 2,4-dimethylheptane. Okay. If you have a tie, again, this is something we've already seen. If you have a tie, which side do you start counting on? You start the side that gives you the group alphabetically. Since I have a tie, this is B, this is M, so we're going to start counting on the right side. So 2-bromo 5-methylhexane. All right, how do you prepare halides? There's several ways that we're going to talk about in this chapter. This is one way, which is radical halogenation. Excuse me. I did tell you that the lab that we did the one lab where we did radical halogenation, and I told you that was going to be the only lab that we were going to do it in. Well, we're going to talk about it one last time just to kind of remind you. And this was a radical formation where the first step is the initiation step. It's the breaking apart of your halogen. All right. Once your halogen breaks apart, all right, what happens is your halide right here, which is the propagation step, okay, remember, is going to react, is going to pluck off a hydrogen, and the other electron will go on the carbon radical. So you'll form your HCl right here, and you form your carbon radical. All right, and then the propagation step now is that this carbon radical now reacts with another equivalent of chlorine. So this reacts with chlorine, okay, to form your product, which is right here, and another chlorine radical, which is right there. So that chlorine radical is basically the same thing as that chlorine radical. That chlorine radical reacts with another one, and it propagates. It keeps going and going and going until eventually you have the termination step. There are 3 possibilities of termination, but really I don't care too much about the termination. I just care that you understand that if you take some sort of alkyl halide plus chlorine in the presence of light, you will get an alkyl-halide. All right, we've also then talked about the reactivities of different alkyl-halides. All right, we talked about that primary is less reactive than secondary, which is less reactive than tertiary. This is nothing new. We've already talked about this. This is just kind of a review about that. Okay. Now, in chapter 4, we learned how to make a dialkyl-halide. All right, we also learned how to just make an alkyl-halide. So these are repeat reactions that we've already learned in chapter 4. Okay, so the first reaction is if you take a double bond plus HX. All right, we learned that the halogen is going to go to the more substituted carbon. And whose rule was that again? All right, if you said Merkabnikov, you are correct. So the X goes here, and the H will go on the least substituted reaction. All right, so that's a hydrohalogenation from chapter 4. Another way is you get the trans dihalogen compound. You form the halonium ion, you remember, in the intermediate, and then your bromine attacks the opposite side. So that was another reaction from chapter 4, and this is a reaction actually from chapter 2 that we just talked about previously. So these are review reactions. These aren't anything new. They're just to remind you that these are ways to make halogens. Okay, this is a new way. In this chapter, this is a new way. The reaction is with an alcohol, so this time we are going to be using an alcohol rather than a double bond. So we're starting with an alcohol, and you're going to add some sort of HX, okay, where X is either chlorine or bromine. Okay, you can do it with iodine, but usually people don't. Usually do it with chlorine or bromine. Okay, this actually shows you that tertiary is much better. All right, so this process of adding HX to an alcohol, really you want to do it on a tertiary or a secondary. The next slide we will see what you can do with primaries. Okay, so the next slide we will kind of see a reaction that works really well with a methyl or with a primary. Okay, but for secondary tertiaries, this reaction works very well. You basically have an HX, okay, and this part forms water. Your OH and your H go off to form water, and your X substitutes the OH and puts an X there. Okay, I'm going to actually do a mechanism on this page. Okay, so let's say we have some sort of alcohol. Okay, and we're going to add, let's say, HCl to it. Okay, first step is the lone pairs from the alcohol protonate and kick out the chlorine. So your oxygen, which remember is partial negative, okay, is attracted to the partial positive of the hydrogen, and the hydrogen actually protonates on this oxygen. So your intermediate looks like this with a plus charge. Okay, plus you have Cl minus floating around. Okay, now if you notice, that looks like water, doesn't it? H2O. Well, it doesn't look like it. It actually forms it. Water is a very good leaving group. It likes to leave. We're going to talk a lot about leaving groups in this chapter. So you form, so if oxygen is going to leave the carbon, what does it leave on this carbon? What charge? It leaves a plus charge. So you form a carbocation. That's why tertiaries and secondaries work really well, because we've learned that tertiary carbocations are much more stable than secondary carbocations. And we've kind of actually learned that you can't really form primary or even a methyl carbocations. All right, those are not very stable. So that's why this works really well for tertiary and secondaries, because you form a carbocation in the intermediate. Once you form the carbocation, your Cl minus now sees that plus charge and bonds its electrons, and you form your final alkyl-halide plus H2O. Okay, so that's the general mechanism. Okay, so go over it again. The oxygen protonates to make a water molecule, which eventually leaves to give you a carbocation. That's why tertiaries and secondaries work really well. Also, allylics and the benzylics. Remember, allylics and benzylics were even more stable than tertiary. All right, just to remind you, allylics and more stable than benzylics. So all these work really well with this reaction. It's just this primary and the methyl will be the reaction that we see on the next page. All right, and then the chlorine comes in, protonates, and you just turn your alcohol into an alkyl halide. Okay? So what reactions work well with primary and secondaries? That is this reaction, SOCl2. Okay? So SOCl2 works very good on primary or secondary alcohol. Here's an example of a secondary alcohol. We are not going to go over the mechanism. You don't have to worry about this mechanism. But basically, the OH turns into a chlorine. All right, and one of these oxygens pair up with the other oxygen to form SO2, and then the hydrogen pairs up with a chlorine to form HCl. But really, I just care about that compound right there. Okay, another one is PBr3. All right, PBr3 does the same thing as SOCl2, but instead it puts on a bromine. Okay, same thing. You want to do this on primary or secondaries. Okay, and we're going to skip 7.3.